Okay, so I'm just going to summarize what I did in office hours with Christopher and Martine. So we were looking at this example right here, number 4. So we have the set of all 2x2 matrices, and then we have the set of symmetric matrices, so Y and Z are equal. And we're going to look at the map from M2R to S2R that takes a matrix ABCD to the matrix ABCD plus its transpose ACBD. So one thing you might want to notice is you can already simplify this expression by saying it's equal to 2a, a plus a, b plus c, c plus b, and 2d. It's the same expression, just sort of simplified. So if we look at this case, t of 1, 2, 3, 4, we get t of 1, 2, 3, 4 is 1, 2, 3, 4 plus 1, 3, 2, 4. And that's 2, 5, 5, 8, which if you notice matches up. So 2a, 2d, so I have the corners, I have 2a, 2d, and then I have b plus c and c plus d on the diagonals. Okay, and I notice that that is indeed a matrix sitting inside of S2R. Then what we did was we looked at part C. So part C is to justify that in general, this is a 2x2 matrix which is symmetric. So now I'm erasing what I wrote down for them because I want to leave it for you guys to do. So you want to confirm here, you want to confirm that whatever T of A, B, C, D is, that it is landing in S2R. So you want to show that the outcome of T has the top left and bottom right symmetric. So if we go back over here, it might be helpful for you to use this expression here. And what you're justifying is that these two numbers will be the same no matter what A, B, C, D you started with. Now we come down here. The first correction that's important is that this is a T, not an F. So if you look at the original, it said F, which was very confusing. This is in fact a T here. So we want to show that T is surjective or onto. So we said, yes, it is surjective. And so we said, well, what does it mean that a map is surjective? It means that for everything in the codomain, remember my T here, my T goes from M2R to S2R, so for everything in the codomain, so an A in the codomain, there exists a B in the domain such that T of that B gets mapped to A. All right? So what does an A in the codomain look like? It's a symmetric matrix, so some X, Y, Z, W in S2R, so Y must be equal to Z because it's a symmetric matrix. And we want to find a B, some 2x2 matrix, so I just called it ABCD, such that T of B equals A. That's what we said here, so it's just summarizing that definition in this context. So T of B equals A, so I'm just going to replace B by B and A by A, so T of ABCD equals XYZW. Now I'm just going to work out what T of ABCD is, so that's ABCD plus ACBD equals XYZW. And so we know that 2A must be X, 2D must be W, and B plus C must be Y, and C plus D must be Z. All right? So that gives us an idea of what A, B, C, and D should be in order to achieve T of A, B, C, D equals X, Y, Z, W. In particular, this tells me that X must be 2A. So since I'm given X, Y, Z, and W, and I have to find the A, B, C, D, what I'm trying to do is solve for A, B, C, and D. So we're stuck with X, Y, Z, W, and we have to choose the A, B, C, Ds. So we get 2A equals X, B plus C equals Y. So one way we could get that is to take A to be X over 2. In fact, I have no other choice for A. A has to be X over 2, and D has to be W over 2. So these two I don't have a lot of choice on. But the B's and the C's, I have lots of ways to choose a B and a C so that they're equal to Y. And remember, Y and Z are equal. So these are really two equations, right, in two unknowns, but the equations are both have to be equal to Y and Z, which are themselves equal. So one way we could do that is by taking b to be y and c to be 0. But then Chris had another way, and that was to take c to be y and b to be 0. And then another way could be to take b to be 1/3 y and c to be 2/3 y and add them, and I would get y. But since all I care about is showing surjectivity, namely, for no matter what A I choose, no matter what X, Y, Z, W I have to find one B. I don't care about having millions of them. We went with the A is X over 2, which I have no choice. B is Y over 2, but then we decided to choose, D is W over 2. And then I chose B equals Y and C equals 0. And I just check that if I take t of x over 2, y, 0, w over 2, you can just check, I get 2 times this, which is x. I get 2 times this, which is w. And then I get y plus 0, which is y, 0 plus y, which is y. And so I get my a back, right? Because y and z are equal. So that's how I get this. And so that tells me it's surjective. But it also suggests that it's not injective, because look, we had the blue way, the black way, and the orange way that we could have mapped to the matrix X, Y, Z, W. So that suggests to me that it's not going to be injective. And then we just remember that if we took t of 1, 2, 3, 4, we got 2, 5, 5, 8. That was back here. Okay. And then we just think, what's another way we could get 2, 5, 5, 8? Well, this was 2 plus 3 was 5. We could switch the 2 and the 3, and we could get 2, 5, 5, 8 again. And since 1, 2, 3, 4 is not equal to 1, 3, 2, 4, these two matrices are not equal, but t of each of them gives me the same answer, 2, 5, 5, 8, then t is not injective. So you see that, as usual, our proof that something is surjective helped us see why it wasn't injective. And so then I did one more example with Martine, and that was going the other way. I'm going to take the set of symmetric matrices to the set of all matrices. Here, I'm going to map the matrix X, Y, Y, Z. It has to be symmetric, so these have to be equal. And I'm going to map it to X, Y minus X, X, Y plus X, Z. So if I take the matrix 1, 2, 2, 4, the x's go to the x's, x goes to x, the z goes to the z, so the 1 and the 4 stay the same. But here, this becomes, for this next term, becomes y minus x. So here that's y minus x, so 2 minus 1, and this is y plus x, so that's y plus x, so that's 2 plus 1. So I get 1, 1, 3, 4. Okay, so we can ask, is it surjective and is it injective? And I'll just tell you for a fact, it's not surjective, but it is injective. But even if we were wrong, even if we weren't sure that it was going to be injective or surjective, if we tried to prove it, if we just tried to prove that it were surjective, then what we would find is the proof would show us that it's not surjective. So let's look at that. And you might want to pause the video and just try and do it on your own and then check back. So hopefully you went and tried to do it, but here we go. So we're supposing we're surjective, right? Then we have a map here. We're supposing it's surjective. That means for everything in the codomain in M2R, there exists something in the domain that maps onto it. So for everything in the codomain M2R, there exists a B in the domain so that L of B is equal to A. Well, what do these A's and B's look like? So A is in the codomain, so it's a matrix, so that's some A, B, C, D. And B is in the domain, so that's some symmetric matrix, X, Y, Y, Z. And what we're saying is that L of B is equal to A. Well, what is L of B? It's just this recipe here. So it's X, Y minus X, Y plus X, Z equals A, which is our A, B, C, D. So now we just look term by term. We say X must be A, Y minus X must be B, Y plus X must be C, and Z must be D. So we got easy ones. X must be A, and Z must be D. And remember what we're stuck with. We stuck with the A, B, C, Ds, and we have to choose the X, Y, Zs. Okay, so let's look at this. It looks like we know what X is, and we know what Z is. And so the only question is, what's y? Well, let's look at this. This is a little bit special. So we've got x is a, z is d, but I've got y minus x is b, and y plus x is c. So let's just solve for y here in both cases. So we get y minus a is b, and y plus a is c. That's a little bit special. So, sorry, I just wrote that down. Here it is. X is equal to a, and this should be z is equal to d. Correct that. This should be z is equal to d. And then what we have is y is equal to a plus b. That's just solving this equation for y. Y is equal to a plus b. And also y is equal to c minus a. So y is simultaneously equal to a plus b and c minus a. Now, if I just give you your average matrix A, B, C, D, and I ask you, is it always the case that the sum of the top row, A plus B, is equal to the same as the difference between these two columns, the elements of the first column? Is it always the case that these two numbers have to add up to the same thing that these two numbers subtract to? That's fairly special. And what it leads us to believe is it's probably not symmetry, because this is some condition that's not always going to be true. It's not always true that for a matrix A, B, C, D, we have that the sum of A and B is equal to the difference of C minus A. And in fact, the first one that comes to mind, if I take 1, 2, 3, 4 as A, B, C, D, I see that A plus B is 1 plus 2, A plus B is 1 plus 2, which is 3, versus C minus A, 3 minus 1, is 2. These aren't equal. 3 and 2 aren't equal. And so that tells me that this matrix, 1, 2, 3, 4, can't be in the image of L. I can't find an A that maps onto it. Okay? Sorry, I can't find a symmetric matrix that maps onto the matrix 1, 2, 3, 4, which tells me that L is not surjective. So now what I think you should do is pause the video again and just check whether or not this is injective. I've told you that it is injective. You might want to think about how you would prove it. Notice that this proof doesn't help you tremendously in deciding whether it's injective. But already when I look at this, I start thinking, that looks like solving a system of equations. Maybe I can do it. So what you need to do in order to start an injectivity proof is to say, suppose I want to show that L is injective. What I really want to do is I want to say, given L of one matrix, X, Y, Y, Z, because remember these are supposed to be symmetric. Suppose that X of Y, 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 Z is equal to L of X, Y, Y, Z is equal to L of R, S, S, T. What do I want to prove? I want to prove that those two matrices are the same. So I want to show that any time that the function L takes one matrix and another matrix to the same place, namely L of the one is equal to L of the other, then those two matrices must be the same. In other words, that X equals R, Y equals S, and T equals Z. So you might want to pause the video and just try this. So I'm going to pretend that you paused the video. And all we're going to do is work out what this would mean and make sure that at every step we have an F and only F. So what we want to notice is that if we have L of X, Y, Y, Z, I know what that is. It's X, sorry, let me get there it is, X, Y minus X, Y plus X, Z. And similarly here it's R, S minus R, R plus S, T. Remember that was the definition of our map all the way back up here. So now we're just going to work out what that means. So we have X is R. We have Z is T. We have Y minus X is equal to S minus R. So Y minus X is equal to S minus R. And we have R plus S is equal to X plus Y plus X. So that's this last equation here. So now let's look at that a little more closely. So I have that X is equal to R. So in this third equation, I can replace this X by an R. So I get X is equal to R, Y minus R now is equal to S minus R, because it was Y minus X, and so now I can replace the X by R. So Y minus R is equal to S minus R, and similarly, Y plus R is S plus R. And now what I notice is I can cancel the r's in both of those equations, and what I end up with is y equals s. So now I have x equals r, y equals t, and y equals s. So that tells me these two matrices are equal, and thus L is injective. That's it.